The first of them is Tomoyuki Yamakami from University, and he will be talking about Oracle from Automata.
Well, thank you very much. I came from University of Fukui. Yeah, I just give it just the tip of the where the Fukui is. You never heard of the word Fukui before. Well, Japan has 47 prefectures. Prefectures is a regional name, and the Fukui is here in this area. It's just kind of the middle part of the Japan. And if you want to go to the Fukui from Tokyo, Tokyo has an international airport. It will take something like 3 hours and 30 minutes to get there. From Osaka, much closer. Osaka is much closer. It's just 1 hour, less than 2 hours. From Kyoto to Fukui, it will take something like 1 hour and half minutes. Okay. So, so this is my second chance to attend SOFSEM. I attended SOFSEM exactly 10 years ago. So year 2004. And that time, the SOFSEM was held in the Czech Republic, and I talked about the title showed like this one. The theory of the one-tape linear time Turing machines. Well, actually, it took me about 6 years to get the paper published, actually. Okay, so today's talk is about the new concept, and I introduced a new notion of the reducibility, and also tonight introduce the hierarchy based on this reduction. And particularly, I'm very interested in the structural complexity theory of the formal languages and automata. So the main result I'm going to present here is the characterization of those language families, and also I'll show a bit of closure property and structural properties. So I start with the motivational discussion. As I said, I'm pretty much interested in the structural complexity theory that is actually based on the formal languages and automata. And in the past, I tried to introduce the several notions or concepts, including the advice, immunity, and simplicity, and the pseudo-random generator against the context-free languages, and the dissectability based on the regular languages, and Boolean hierarchy over CFL, context-free languages. And this time, I'm going to introduce two reductions. One of them is called the many one reduction, and another one is the Turing reduction. And based on those reductions, and I'm going to make a relativization. And that actually help create the hierarchy over the CFL. So I start with the many one reductions. The basic model for this reduction is the pushdown automata, non-deterministic pushdown automata. So this is actually pretty much that, what you actually see the picture, basically it's in any textbook about an automata theory. And I add query tape. So this is the write-only tape. And you can actually write down the string on this tape, query tape. And we have external device or external information source called an oracle. This is actually a set in the mathematical term. And a string written down on this query tape is transferred to oracle. And the oracle actually makes a decision whether yes or no. And the answer, the oracle modifies the inner state of the basis machinery. So this is actually the basic model of the computation I'm going to use. And now, I'll just give it a formal notion of the reduction, the many one reduction. I just abbreviate it as an M reduction. So the reduction, the machine is called M reduction NPDA, or just simply call it Oracle NPDA. So this is the pretty much similar to the previous one, the standard one. The only difference is the write-only query tape, and also the definition of the transition function is different, because that includes the oracle or query tape. An important condition I'm going to impose on this machinery is the termination condition. You are aware that all context-free languages, the basis for the context freeness is guaranteed by the non-deterministic Pushdown automata. But then you cannot always design the machinery to run in linear time in terms of the input size. So it is. Go ahead.
Why should it reject? I mean, it's just non-deterministic, and if we just stop, why should it say I?
Yeah, it could
It should
be.
accept if it is in. Yeah, that I completely agree. But why should it reject if it has not get the conclusion? So it was
Well, that is
simply
another
dying
way
out.
to define the non-determinism. But in a polynomial time setting, it doesn't matter whether you actually cut down the whole computation in the polynomial time, because internally you can actually
Yeah, I
input.
understand.
Yes.
I'm just objecting that it should reject. It just stops and says nothing.
Well, yeah, that is another way, but I'm not going to take that definition. I'm asking that all the computation have to be terminate. That is controlled by an algorithm inside the machine. Okay? Because that actually caused a lot of trouble, because that's actually unintentionally give the machinery to be too strong, too powerful. So that, well, maybe if you think about it, that is maybe tonight, maybe you can find out how strong it will be. So that's why I just put this condition, and I use the notation ACCM of X to be the collection of the accepting computation path. So this is the formal definition for the many one reduction. And suppose an L is the language of the alphabet stemmer, and A is a language, another language over theta. And L is called the many one CFL reducible to A. A is also called the oracle. And we actually have the M reduction NPPA or oracle NPPA machinery. And that satisfies the following two conditions. So as you see, the machinery actually produces the string, the query word. We call it the query word. That string that is actually written down in the query tape. So that has to be in accepting path, not the rejecting path. So that the machine control that whether this is actually query word, the valid query word, or not. And the condition, this is actually the typical many one condition. If input X is in L, if and only if there is an accepting path, and the query word along that accepting path has to be in A. Okay, so for notational simplicity, and I just write it down. So L belongs to CFL sub N to the A. And for the language family, F, I just extend, just making the union of all possible CFL to the A, and A belongs to N. I'll give you some examples. The first one is a very simple one. I can possibly make it, give you a very complex one later on, but the first one is the very simple one. That the duplication, that's the XX. So you know that this language is not context-free, but this language itself is a many one CFL reducible to a particular language called A. The A has this form, X to the R, so that's in reverse, and sharp. Sharp is the fresh symbol, not in X, and X. So X, reverse, sharp, X. So you know this language is CFL. The reduction is very simple. So as you see, the algorithm like this one. I just explained this one more carefully. So suppose we are given the input, say W, 1010, for example, and then it's non-deterministically, so we actually split it or pass it into X and Y. And then the X part, we just use the stack to reverse it, and then to write it down on the query pin, and then just to copy the line, including this pound symbol. So we actually get those things on the query pin, but those are actually different branches. Now, you actually make a query. And the oracle actually determine receiving this the query word, and oracle make a decision whether this is actually in A or not in A. The answer is yes or no. then this is transferred into the machinery again. So the machine actually said if the molecule answers yes, then it should accept. Otherwise, reject. So, but then if you're actually wondering whether this is just an algorithmic description, so I just simply write it down. The actual formal description of the transition function is very simple, like this one. So I will give you two more examples. The duplication, well, 3 copies, x. We just simply use the different oracle, x to the r, pound, x to the r. This is also the context-free operations. And what about the matching? So the x, the first part, we have to judge whether the first part x has to be in somewhere in W or not. So this is also reducible to xr pound x, the exact same one we use. So the conclusion here is that we can actually reduce the non-context-free languages to the CFL. So that means the CFL to the CFL is much bigger than CFL alone. So this situation is completely different from in the polynomial time setting, because in the polynomial time setting, NP to the NP is equal to NP. Right? Now we see that the CFL situation is completely different. So I'll give you one more example. That is slightly more complex case. So the square, the length, 0 to the n, 1 to the n squared. So now you have to judge whether the 1 has n squared, meaning, the latter half of the n has the n squared, many ones. So this is also non-context free, but they're reducible to this particular language. This is in CFL. So this is has the forms 0 to the I, 1 to the J1, and 1 to the J2, and so on. And the length of the consecutive or adjacent number are exactly the same. And I is the same as the total number of those ones, blocks. And this is done by the molecular machinery described by the following way. So that the input W, we have first to check out the input has the form like 0 to the I, 1 to the J, or some number I and J, and simultaneously we have to guess, or non-deterministically pass the J1, J2, and so on, satisfying those conditions. And now you see that we actually generate the W prime or this form. But at this moment, we are not sure that the W prime is actually in this form D or not. So we just need to make a query to Oracle, and then Oracle will actually determine whether the W prime has exactly this form. So that's it. So now I'll give you the characterization of the CFL to the CFL. We will use. I'm going to use the language called the deep language. Deep language is the kind of extension of the balanced parentheses described by industry. So I'll use the capital letters in the DYCK dig to represent all deep languages. The theorem, or the lemma says the CFL to the CFL is exactly the same as the CFL to the deterministic CFL, and also as CFL to the deep languages. And also the base machinery in CFL can be modified or weakened to be non-deterministic finite automata without any slack. But still we have the same power. So that the very nice calculation. And as we have seen that the CFL to the CFL is not a CFL. That means that if you just apply the CFL as some sort of the operator, then it actually grows from the base case. So that suggests that we can actually apply the minimum reduction k times. Right? And the k would be an arbitrary natural number. Then we can possibly get into a much bigger complexity class. The characterization here says the CFL to the CFL, then we applied the K-many application of the minimum reduction. So that is exactly the same as the CFL to the CFL of K. The CFL of the K is the K conjunctive closure of the CFL. That is the basically K-many intersection of the CFL. And we know that this actually has the informing. Okay, yeah, well we have that discussion sessions already. Infinite hierarchy, that is proven by the 1973. So at this moment, we have we explained this this area here and then this area here and then those things. So now we move on to the Turing reduction. So I have to speed up a little bit. The Turing reduction is actually pretty much the same as the minimum reduction, but the only difference is we have the three extra internal inner states, the Q query, the Q yes, and Q no. And the transition function is accommodating those extra three inner states. And we also require the termination condition. So the basis machinery have to terminate. I'm talking about all possible computation path. Have to terminate within linear time, no matter what you get. And the computation goes like this. So this is more pictorial description of the computation. So that now we will get the input x, and then the following the non-deterministic path, and then some certain moment we just simply write it down the query word, and then just go into the query state. So that the string is transferred to the oracle, and the oracle decide, and then to modify the inner state, Q yes or Q no. Then so important thing is the query tape is automatically reset. That means I got blank, and then head actually automatically move back to the initial position. And the computation goes on and on, and until they actually decide to accept or reject. So that's the Turing reduction. Then the Turing reducibility is defined pretty much the same as before. If x belongs to L, if and only if M goes into the accepting state using this OR mechanism. And also we have to. The important thing is the termination condition have to be satisfied. We use the notation similar to the before, the CFL to the A, but then we just put the P to emphasize that we actually use the Turing reduction. Now, I'll just give you another characterization for this Turing reduction. CFL to the CFL is exactly the same as CFL to the CFL sub 2 using a minimum reduction. And what is the CFL sub 2? That is actually the Boolean hierarchy over the CFL. The Boolean hierarchy is actually created by the AND operator and the OR operator. And particularly if you look at the CFL2, that is the intersection of an A and B. An A comes from the CFL, B comes from the complement of the CFL. Okay, and also the basis machine can be changed into the NFA. Okay. So I added the extra complexity classes around here and here. So we have defined the minimum reduction and also the extension of that for the Turing reduction. So we will use the Turing reduction to create the hierarchy of language families. So the hierarchy is pretty much the the analog of the polynomial time hierarchy. If you are aware of the polynomial time hierarchy, the basis, the first level is exactly the deterministic CFL and CFL. But if you go up higher, then for example, the sigma k plus 1, that is defined using the sigma k oracle and using a Turing reduction. And the pi is actually the complement of the sigma. And this is a very interesting the set of complexity classes that satisfies the following thing. For example, the oracle part, it doesn't matter if you're actually using a sigma oracle or pi oracle. And k's level is included in the k plus 1 level, so that if you go up higher, and if you just go up the levels, and the level actually contains the form. And the important thing is that the whole entire hierarchy is actually sitting inside the deterministic linear space. So the classes are not that big. And also this hierarchy satisfies the following closure properties, like concatenation, the union, the reversible, and the substitution, and homomorphism, and so on. They're just a standard closure property. But the important thing here is that we are actually using the length non-decreasing and the lambda free requirement. Basically that says, for example, lambda free means lambda is an empty string. So the homomorphism does not output that empty string, that kind of thing. And for the first level, we know that this class is not closed under intersection and also the complementation. But I'm not quite sure about the second level, third level, and so on. So that's still open question. So we have seen several examples, like a dupe 2, dupe 3, and square length, and those are actually nicely snugly into the sigma 2, second levels in the sigma higher, sigma level. But the prime length, that means the 0 to the n has to be the prime number. So this going to the pi is the complement of the sigma. So those complexity classes goes in this way. Okay. Oh yeah, I'm going to finish it. So finally, so now I'll just give the structural property. So we have seen it in the closure property, and now I'm just explaining the structure. The structure property here, the theorem says if the k plus 1 level collapses to k, so that some certain level collapse, then entire hierarchy collapses down to that level, and vice versa. And if you have the sigma level to pi level collapse together, the Boolean hierarchy built over the sigma k collapses. And additionally, those two statements, the first two statements, are exactly the same thing. So that means, whatever you just make a collapse, and then everything collapses. That's a really nice situation. So finally, okay, so I'm going to give the open problem, so that if you are really interested in this field or this topics, maybe you can actually dig out a little bit and then just write a nice paper. So the first one is try to prove the separation between some certain level of hierarchy. But this seems to be this is relatively easy to compare to you actually attempt to the collapse, because the collapse of a certain level implies the collapse of the polynomial hierarchy. And also, it's very nice to find the relationship between the circuit boundaries. Like AC0 to the sigma 1 is the semi-bounded AC1. And maybe you can find out in the relativized world. So, simple example is that the bounded error probabilistic CFL is not contained in the intersection of the sigma 2 and the pi 2. And in the polynomial time level, this never happens. So this is really, particular about the CFL. The another one is that maybe we just simply consider the pseudo-random generator again, the sigma k, and also the dissectability. So that you just cut the language into half. And those are actually written down in some extension in my previous work. And thank you for listening, and I'm going to take your questions.
Thanks for the nice talk. There is time for one short question. First.
What about language emptiness?
That is the. Okay, so you're talking about the given language, and then you have to judge whether this is empty or not. So that is a really difficult question, isn't it? It's not in this hierarchy. Because all the hierarchy, the language that belongs to the hierarchy is just below the D space N.
No, I'm sorry, we have time, so you can talk together in a couple minutes, yeah?
Okay, thank you very much.